Let's get into the example problems so that you know how to graph these on your own. Now this is not the parent function anymore. This is graph y equals 3 to the x power. Alright, basically this is a skill of using your calculator. Handy dandy calculator, you guys have to share them. We don't have enough. Anyway, my table, I'm just going to start labeling it the same exact way I have done before. And then I'm just going to go ahead and use substitution. Here we get y equals e to the 3 times negative 2 is negative 6. Alright, that means in my calculator I'm going to be plugging in e to the negative 6 and I'm hitting enter. That's about 0.0025 if I round up. Okay, now if I plug in negative 1 into my function, that's y equals e to the 3 times negative 1. That's negative 3. I'm going to just go ahead and use my calculator and plug in negative 3 there to get about 0.0498 if I round up. Alright, and then we get y equals, and then 3 times 0 is just 0. So e to the 0, which is just 1. Alright, now let's plug in 1 into my function. So y equals e to the, and then 1 times 3, that's just e to the third power. Again, I'm going to be using my calculator to find out what e to the third power is. It's going to be a positive large number. That's about 20.09 if I round up. And so forth. So then y equals e to the 3 times 2 is 6. E to the 6 is going to be humongous. Quite honestly, it's probably not even going to fit in our graph. Yep, 403. Oh yeah, by the way, guys, as you can see, exponential graphs grow really fast. So as you can see, it already hit into the hundreds. So that means next up we got y equals e to the 3 times 3 is going to give me e to the 9. So second to the 9, humongous number. About 8,103.1 if you round up. Okay, obviously those two last points aren't going to fit in our graph. Whatever, we're going to make an approximation though. For the ones that do fit in your graphs though, they should be accurate. So here we go. So when x equals negative 2, you get 0.0025. Again, that's a humongously tiny number. I'm just going to put a dot very close to the x-axis. When x equals negative 1, you get 0.0498. Again, very tiny. I'm just going to put that very close to the x-axis again. But then I do know it's slightly higher than the previous number. When x is 0, you just get 1. When x is 1, you get 20.09. You get that this shoots up into the 20s range. And when x equals 2, you're going to get off your graph. So this is what this one looks like. So at the end, these right here are off my graph. That's what I would like you to do if I give you a function that just shoots out of your graph range. And then try to your best of your ability, make a function that looks, and again, this is going to approach the x-axis but never touch it. Yep, it's just growing way much faster than the other one. It looks like so. It's very fast. Okay. Well, now let's go on to example 2. It's different. It has y equals e to the negative 2x. So let's see how we would graph that one. Just this. All right. Graphing y equals e to the negative 2x. Well, let's go ahead and label our graph the same as we would. Just usually choose points around 0. If you don't want to make your own choices, choose the same ones I did. Let's go ahead and use substitution again. Y equals e negative 2 times negative 2 is positive 4. So for this one, we're trying to evaluate e to the 4th power. Handy dandy calculator. Enter. You get 54.6. Again, this is going to be off my graph, but that's okay. You will be expected to graph the ones that are on your graph. Anyways, next up, y equals e. Negative 2 times negative 1, that's e to the positive 2. Using my calculator. Hold on a second. Anyway, as I was saying, e to the second, you would use the calculator. Again, you're going to have to share it. E to the positive 2, and you click enter, you get 7.389. Cool. I think we've had that value before. Next up, y equals e to the negative 2 times 0. So negative 2 times 0, that's just e to the 0. You just get 1 here. All right, let's plug in 1 into my function. So y equals e to the negative 2 times 1 is e to the negative 2. Using my calculator, let's figure out what e to the negative 2 is. It's about 0.1353. All right, let's go on now. So y equals e to the negative 2 times 2. That's going to be e to the negative 4th power. I would use my calculator, and I'm already imagining that's going to be a tiny number. Yeah, 0.0183. And by the way, guys, I knew it's tiny because it's large here, and then it's getting smaller. Next up, let's plug in 3 into my function. So y equals e to the negative 2 times 3 is negative 6. So second, e to the negative 6 is going to be a very, very small number. 0.0025. There we go. So we've got our points down. Now, well, let's see how this graph looks. And let me tell you something. This negative in the exponent will change the way our graph looks. Let's begin. All right, so at x equals negative 2, you get that y is 54.6. So at negative 2, this is a humongously huge number. It goes off our graph. I'm just imagining, I just drew a dot right over there. Okay. Now then at x equals negative 1, which is right here, we get 7.389. Now 7 was around here. Okay. When x equals 0, you get 1. Y is 1. When x equals 1, you get 0.1353. That's a number less than halfway. When you get 2, that's a number even less than this previous number. So again, it's getting closer and closer to the x-axis. And then when it's equal to, when x is 3, it's even smaller. So it's just getting closer and closer. The inching into the x-axis is so close that, you know, you just got to approximate it once it hits there. So let's go ahead and try to draw a sketch. And you want to try to make it smooth. Try not to have sharpness going on. It's great if you have a pencil. If you have a pen, well, good luck with that one. Because I would mess up if I had a pen. Then I'd... So again, for the points that are on your graph, you are expected to show accuracy. There we go. So take a look at the difference between these. They kind of switched, right? They switched directions. Basically, if you look at example 1, it's drastically increasing very quickly. And if you look at the graph of example 2, it's drastically decreasing very quickly. So that's the differences between these two graphs. And that's using the base E. Again, E shows up a lot of places in the math world. Hopefully we get to talk a little more about these. But by the way, this point was off my graph. I will like you to also tell me in your task which points ended up going off your graph. Because that's going to let me know that you understand how to approximate the points that are on your graph, okay? Well, good luck.